In number theory, a Gaussian integer is a complex number whose real and imaginary parts are both integers. The Gaussian integers, with ordinary addition and multiplication of complex numbers, form an integral domain, usually written as Zi. This integral domain is a particular case of a commutative ring of quadratic integers. It does not have a total ordering that respects arithmetic. Formal definition. Formally, the Gaussian integers are the set. Note that when they are considered within the complex plane, the Gaussian integers may be seen to constitute the two-dimensional integer lattice. Norm of a Gaussian integer. The norm of a Gaussian integer is the square of its absolute value as a complex number. It is the natural number defined as where is complex conjugation. The norm is multiplicative, since the absolute value of complex numbers is multiplicative, i.e., 1 has the latter can also be verified by a straightforward check. The units of Zi are precisely those elements with norm 1, i.e., the set plus or minus 1, plus or minus I. As a principal ideal domain, the Gaussian integers form a principal ideal domain with units plus or minus 1, plus or minus I. For x, z, I, the four numbers plus or minus x, plus or minus 6 are called the associates of x. As for every principal ideal domain, Zi is also a unique factorization domain. The prime elements of Zi are also known as Gaussian primes. An associate of a Gaussian prime is also a Gaussian prime. The Gaussian primes are symmetric about the real and imaginary axes. The positive integer Gaussian primes are the prime numbers that are congruent to 3 modulo 4. One should not refer to only these numbers as the Gaussian primes, which refers to all the Gaussian primes, many of which do not lie in Z. A Gaussian integer a plus by is a Gaussian prime if and only if either one of a, b is 0 and the other is a prime number of the form 4n plus 3 or its negative minus, or both are non-zero, and a2 plus b2 is a prime number. In other words, a Gaussian integer is a Gaussian prime if and only if either its norm is a prime number, or it is the product by a unit of a prime number of the form 4n plus 3. It follows that there are 3 cases for the factorization of a prime number p in the Gaussian integers. If p is congruent to 3 modulo 4, then it is a Gaussian prime. In the language of algebraic number theory, p is said to be inert in the Gaussian integers. If p is congruent to 1 modulo 4, then it is the product of a Gaussian prime by its conjugate, both of which are non-associated Gaussian primes. P is said to be a decomposed prime in the Gaussian integers. For example, 5 equals and 13 equals. If p equals 2, we have 2 equals I2, that is, 2 is the product of the square of a Gaussian prime by a unit. It is the unique ramified prime in the Gaussian integers. As an integral closure, the ring of Gaussian integers is the integral closure of Z in the field of Gaussian rationals Q consisting of a complex numbers whose real and imaginary part are both rational. As a Euclidean domain, it is easy to see graphically that every complex number is within units of a Gaussian integer. Put another way, every complex number has a maximal distance of units to some multiple of Z. Where Z is any Gaussian integer, this turns Z into a Euclidean domain. Where historical background. The ring of Gaussian integers was introduced by Carl Friedrich Gauss in his second monograph on quartic reciprocity. The theorem of quadratic reciprocity relates the solvability of the congruence x2q to that of x2p. Similarly, cubic reciprocity relates the solvability of x3q to that of x3p. And biquadratic reciprocity is a relation between x4q and x4p. Gauss discovered that the law of biquadratic reciprocity and its supplements were more easily stated and proved as statements about whole complex numbers than they are as statements about ordinary whole numbers. In a footnote he notes that the Eisenstein integers are the natural domain for stating and proving results on cubic reciprocity, and indicates that similar extensions of the integers are the appropriate domains for studying higher reciprocity laws. This paper not only introduced the Gaussian integers and proved they are a unique factorization domain, it also introduced the terms norm, unit, primary, and associate, which are now standard in algebraic number theory. Unsolved problems. Most of the unsolved problems are related to the repartition in the plane of the Gaussian primes. Gauss's circle problem does not deal with the Gaussian integers per se, but instead asks for the number of lattice points inside a circle of a given radius centered at the origin. This is equivalent to determining the number of Gaussian integers with norm less than a given value. There are also conjectures and unsolved problems about the Gaussian primes. Two of them are: the real and imaginary axes have the infinite set of Gaussian primes 3, 7, 11, 19, and their associates. Are there any other lines that have infinitely many Gaussian primes on them? In particular, are there infinitely many Gaussian primes of the form 1 plus key? Is it possible to walk to infinity using the Gaussian primes as stepping stones and taking steps of bounded length? This is known as the Gaussian mote problem. It was posed in 1962 by Basil Gordon and remains unsolved.